So now what I'm going to do is I'm going to say I want a voltage drop across here. So I'm going to find the voltage drop across there. I'm going to go V equals Q over C. The charge we just said we're for sure at 15.6. What's the, that's 2, right?
Wait, I see how you got that equation.
Okay. So that's 7.8 volts is dropped going across here.
I mean, all right.
Okay. So now I need to drop, what do I need to drop to get it from here, from this spot to that spot? Oh, waiting.
I don't understand. Okay, this is wrong. Because
What?
you can't, you're mixing like the specific voltage for that scenario with the total charge of the entire
I know
circuit.
there's 15.6 coulombs on this capacitor. How do I know that?
I don't know.
Whatever came off of these plates, sitting on that plate there, right? Whatever came off these two plates has to be right there.
But between 3 and 4, is there another 15?
It's the same 15.6 stored.
For all of them?
It's the same 15.6.
Whatever.
This is negative 15.6. This is positive 15.6. When you discharge, the electrons are going to flow back here and neutralize this. So you essentially it's this plate and this plate that are 15.6 where the charge is useful. These two plates are going to do nothing. They're just going to restore it. You're not getting the charge from inside these two plates.
All right.
Okay. All right. So 7.8 volts. So what's left over to drop from here to here?
7.8. Negative 7.2.
2.2 volts, right? I used up 7.8 volts, used up on just to get this thing powered, which means there's 2.2 volts left here.
Yeah.
Okay, yes, sir?
If you use Kirchhoff, would you have to also still solve for the charge?
You would. You have to say, but you'd start at Q1 is equal to Q2 plus Q3. That's would be the same thing as the current statement, right? That's the game we play. Yes?
So my thing is that does not equal 15.6 when added together.
What does it?
The voltage.
It's supposed to add 10. Should add to 10.
Oh, shoot.
So 2.2 plus 7.8 adds up to 10.
Oh, okay.
Yeah. And so now I'm going to do these two. Now, these two charges had better add up to 15.6, so we got problems. Right?
Wait.
These two,
I thought we just decided that there's only 2.
there's 2.2 volts.
Okay.
Now I got to find charge, right? So I'm going to go CV equals Q. But since they're in parallel, each one gets their own, right? So I'm going to go capacitance is 4, 2.2. I get my charge going this route is going to be 8.8 coulombs, right?
That's what I got.
Going the other way, I got 3 times 2.2 equals Q. And that gives me 6.6 coulombs. Now these two should add up to the 15.6, do they? Add up to 15.4. There's some rounding going on here. It's a little shaky.
It's all good.
Not quite right.
I mean,
Okay. Now, right. I'll leave that off because we can discuss that on the next one. Does that make sense? Can we do this? This idea, how the charge is set up, and what the idea is going on? Yeah.
Just like a few questions.
Yes.
Okay, so it says another little box parallel. How would that
Like over
affect-
here,
No, farther down the little line.
like put it in the box parallel.
Yeah.
So it would be.
Annex.
So you'd have to do these two together, and then the whole thing in series.
Right, but how does the charge,
Add these two.
How do the
add these
charges
two.
interact? Because
Oh,
can't be.
then things get interesting. All lumps have to the same charge, right?
Yeah.
Because the plates, sometimes on this plate, have to go to this plate.
Yeah.
That causes this plate to create that plate.
But which ones are negative and positive and what's
Well, with attached to negative battery, it's going to be negative. So that's going to be a negative plate. That's going to be a negative plate. This is going to be positive. This is going to be positive, which means this thing picked up negative because the electrons were fleeing. That's what made these positive on this plate right here, and that makes this positive.
But like each individual, like isolated part of the series
Has to have the same charge.
has to have the same charge.
Has to have the same charge because they're always coming from the plate in front of them.
That seems important.
They don't have a choice. It is important. That's hugely important. Okay. All right. Everybody contemplate number 8, which doesn't have an 8 on it, but figure it out anyways. It's 8. Close S1, then answer. And then once you're done closing S1, you're going to then pop S1 open at the same time you're going to close S2 and tell me what happens after that. And that's the one that's kind of new and thoughtful. And by the way, something appears on the AP test like every friggin' time. Situation 2, we pop the other one. This is at 2 farads. We got 4 farads over here. So first of all, which one is easier to store charge on?
2. Wait, what?
Capacitance to store charge.
Easier?
Easier.
Okay, 4. Because
4. You get more charge for the same voltage, right? CV equals Q. Okay? So, this starts off as 20 coulombs. Now, what's going to happen? Well, I've got a bunch of negatives here. I got a bunch of positives here. Current's going to start to flow. Electrons are going to start flowing this way until they get to this plate. Once electrons hit this plate, they're going to be stuck to that plate. But what happens? Electrons are going to start leaving this plate, and they're going to reduce the positive charge over there. Right? That's going to continue until what happens?
It establishes an equal.
Until it runs out. There's no charge being lost here. There's no running out. What happens when, what is going to trigger this thing stopping?
Oh,
When
the
it reaches
voltage
equilibrium.
The voltage runs, not the voltage runs out, the voltage are
used up.
equal. In other words, the voltage pushing the current out of here is equal to the voltage stopping the current from getting on this plate. Okay? So V of the 2 is going to be equal to V to the 4. Right? So both VC equals Q. So we don't like this formula because that's a bad formula. So V equals Q over C. That's the formula we should have on our formula sheet. Oh, no, we have it for reverse. Never mind. Whatever. Okay, so Q over C is equal to Q over C. Right? And this by the way has 2 and this has 4. Do they have the same charge on them?
No.
No, they can't, because one of them makes it easier to have, right? So I'm going to call this Q the 2 one. I'm going to call this Q on the 4 one. Which means we have 2 unknowns, don't we? So the current's going to drive until our voltages are equal.
Wait, what did you just write up there?
I made those subnotations. Q2 over 2 equals Q4 over 4.
And the 2 and the 4 are the
Capacitance, right? Because the formula for voltage is equal to Q over C, right? So I simply said the charge over the 2 one is equal to the charge over the 4 one. Unfortunately, that left me with 2 unknowns. I need another equation.
Does the total charge matter?
Does the total charge matter? Explain that.
Energy.
Does the total charge matter?
Didn't it split equally before between each little area?
It doesn't, because although it had 20 coulombs on this thing, we just said that because these plates are bigger, because a 4 versus a 2 farad capacitor, there would be more charge. There would be more charge for less voltage over here, right? And the current would drive until the voltages are the same.
Yeah.
But your answer to the question was the right answer. You just used it the wrong way. Does the total charge matter? Yeah, that's what's driving this thing, isn't it? The fact that you had 20 coulombs to begin with. Some of it's going to be on this plate, and some of it's going to be on these plates. And unlike before, they don't have to be equal, right? Because we started with an equal amount of charge to begin with, right? Instead, they're going to have to add up to 20. So the second statement is Q2, Q on the 2 plate, plus Q on the 4 farad capacitor has to equal 20. Because that charge is being redistributed between the 2 capacitors, right? 2 equations, 2 unknowns, you can totally solve that.
Wait, but see, if you use the equations to find the charge and you know this one you know about,
Uh-huh.
you get like 13.
You get 13.
Yeah, because if you say...
What's the voltage you
Because
used?
you just say that...
What's the voltage you used?
10.
Okay, there's not 10 volts when this is done. The battery's
Okay,
off.
that's
I
what I got.
popped the 10-volt battery for the 10 volts.
But 2F has 10.
Once the electrons start leaving, listen, your questions are, by the way, excellent, because later on I'm going to ask you what's happening, and you're going to have to give me back these ideas, not numbers. The equations won't do it. Once the electrons start leaving this plate, what happens to the voltage of it? It goes down. The voltage of the system is going to start going. This can't remain as a 10-volt battery because the only reason it has 10 volts is because there's charge on it. Once charge starts leaving, it loses voltage.
So, but can you say that about a battery then? Like,
No, because batteries are specially made by the magic physics people in physics land that they continually give you the same voltage no matter what you do to them. Which, by the way, is strictly speaking not true. They act like capacitors. They actually act like they also have resistors in there. They do act like these things. We work very hard to make that 6-volt battery basically put out 6 volts for a very long time. And it does. I mean, it does. It starts at 6.5, and eventually 6.4, then 6.3, then 6.2, then 6.1, then 6.0, 5.9, 5.8, and then suddenly, like, it starts dropping like there's no tomorrow because the chemicals aren't enough to get over the threshold. But they're designed specifically to put out roughly 6 volts as long as we can possibly pull it off. But you're right, it's basically a capacitor, with the chemicals allowing us to add more electrons to the plates.
So capacitors can't hold voltage.
Once they start losing charge, they're losing voltage,
Okay.
right? Because they always have voltage is because they're charged. That's what stops current from flowing through them. Got it?